Okay, for the folks here who missed the last 2 minutes of lecture last class, I'm just going to do a super quick review without the mechanism because we're not going to worry about the mechanism on let's try this here. Here. Ozonolysis, super useful technique because one of the strategies that we're going to start using a lot of in synthesis style problems is you're going to want to be able to manipulate structure or add functionality so that you can do subsequent chemistry to those locations. So we haven't got any mechanisms for adding carbons to the carbon chains yet, but anytime you are able to add a carbon, for instance, or link carbon chains, that's going to be pure gold synthetically. This is another technique that's actually super useful, and whenever you have an alkene and you treat it by bubbling ozone through at minus 78 degrees Celsius, what you functionally do is cleave the alkene and you add a double bonded oxygen to both carbons. So the outcomes of this are pretty varied, and this will happen to all alkenes. If you have a cyclic structure and you treat this with ozonolysis, you'll cleave here and you get 1, 2, 3, 4, 5, 6 carbons with aldehydes on both ends. And one of the things I forgot that we hadn't really discussed yet are functional groups, including aldehydes and ketones. So we're not going to be doing the chemistry of aldehydes and ketones this semester. We're going to save that for next semester. But an aldehyde is a carbon with a double bond oxygen and a hydrogen. And a ketone is when you have a pair of carbons attached to the carbon which has the double bond. So in this case, we end up with a pair of aldehydes because we don't have a carbon on both sides. If we had a scenario like this, where we have a carbon, carbon, and carbon of different identities and a hydrogen, and we could call this Ca and Cb. Ca is going to be a ketone, and Cb would be an aldehyde. So in terms of predicting structures. And of course, if you're non-cyclic, you're dividing, you can cleave off a whole compound. So if we've got something like this, and we treat with ozonolysis, you're going to end up with 2 compounds, 1, 2, 3, 4, both of which are aldehydes in this case. So this can get it can be really useful, or it can get really messy, and you can start cleaving things that you don't want to. So every now and then it's nice to be able to add groups like this in the place, bless you, of just alkenes. Sometimes we're going to find that these are really great for subsequent nucleophilic attacks down the road. So that's what you guys missed on the video. And funny thing, I was lesson planning last night, and I realized I totally skipped one of the mechanisms.
Yeah.
I remember thinking when I was moving through the lecture, man, I'm making a really good time today. It's because I was skipping things. So we're going to take a step back and look at the formation of vicinal dihalogens real fast. Well, not that fast. We're going to take our time with it. So what we've been doing in terms of additions of halogens include halohydrides, right? Where we've got this dipole, and the nucleophile comes in and attacks here, kicking off the bromine. The bromine does a subsequent and second attack. Well, what we can do is actually just add bromine or chlorine gas across a double bond too. And this is a little bit limited. It doesn't apply to all the halogens because the product with iodine is not stable, so you can't do this with iodine. And if you try to do it with fluorine, it's explosively reactive, so it's not feasible. So because of that, this particular reaction we're about to do is limited to just Br2 and Cl2. So what this looks like overall, let's see. If we have some generic alkene, and notice that this is intentionally designed with a little bit of asymmetry to it, where we have a more substituted carbon and a less substituted carbon. And we add, say, bromine gas in this case. To do this reaction, we have to use an inert solvent. This is dichloromethane, CH2Cl2. And by inert solvent, that means it just can dissolve everything that we need to dissolve so that everything's in the reaction mixture together, but it doesn't participate in the reaction. What we're going to find down the road in just a minute is that if we have water or an alcohol or anything like that in here, that's going to participate in secondary reactions. So we want to have that inert solvent. And we have freedom of rotation around that bond, so I'm not showing any kind of stereochemistry in the product. Now, this is called a vicinal product because we have both of the bromines right next to each other. Let's look at how this happens mechanistically, and we'll be able to get some of the advantages of this approach in just a second. So let's say we've got I'm going to change this up. I'm going to make this asymmetric. So this is still going to act as our nucleophile. And what happens is bromine comes in, and we're going to get a concerted reaction where we're going to get our first nucleophilic attack from these pi electrons coming up and attacking the bromine. These bromines are going to then come down and attack this carbon. This is going to exceed the number of bonds allowable on this bromine, so these electrons are going to move up to the top bromine, breaking that bond. And this can happen because the bromine's pretty content as a halogen getting that extra electron and getting that charge because it gets its noble gas configuration. So it's a decent leaving group. And what we get as an intermediate is this three-membered ring to the bromine with a positive charge and a bromide anion. So when we see this, everyone at this point starting to queue up, okay, well, we know that bromine prefers to be negatively charged, so putting a positive charge on it is going to make it particularly apt to receive electrons. We also know the three-membered rings are strained, so 60 degrees is not anywhere near that sp3 hybridization's ideal angle. So it's going to be very easy to do an attack on one of these two carbons to open up this ring and push the electrons from one of these bonds to the bromine, and that's going to make everything a lot happier. Now, the question is which carbon is going to get preferentially attacked? And ideas on that. You guys like the secondary carbon? Why?
It's less stable.
The secondary carbon's less stable.
The one that has the most hydrogens on it is less stable. So
If you form a carbocation,
we're not doing that.
are we? We're not?
You
Kind of?
can.
Kind of? Maybe? We're on the right track. Okay. So, this is so electron withdrawing because of that positive charge on the bromine that is going to be attempting to pull electrons very aggressively towards this positive charge to help satisfy it. And by doing that, it's going to form some cationic partial positive character here and here. Now, where is it going to be more effective at forming the partial positive character? On the secondary carbon, because that can support that cationic character more easily because of the hyperconjugation. So we're going to get a greater partial positive charge here than here, which is going to make it overwhelmingly favored for the second attack. When these electrons come in here, attack this, we're exceeding our octet because we can't have 5 bonds to carbon. So the easiest bond to break is this one. Sends those electrons up to the bromine. I think that is our product. Yeah. So, a couple notes about this. We're going to get into it at the end of the chapter a little bit more detail. But one of the characteristics of this reaction is that these result in an anti-addition. The bromines come in from opposite sides. So the first attack happens from one side, and then because you have this ring structure, the second attack comes in from the opposite side. So if we are doing this reaction on something where we don't have free rotation, you're going to have a mixture of products, but the bromine is going to come in from opposite sides of that ring structure. Yeah?
Can you explain why it's an oxidative reaction?
Why it's an oxidative reaction? So that's probably stemming from that homework question where the HBr was non-oxidative and the Br2 was oxidative. This is a wild guess.
Yeah.
Okay. I think what they're looking at in the homework is the total of all the oxidation numbers of the system. And when you have HBr, this is electron rich and this is electron poor. So they kind of balance out the oxidative numbers when they do the addition. One group is bringing more electrons, one group is housing existing electrons because of a deficit, and so it kind of works itself out. When you have two halogens, they're both bringing extra electrons to the party, which is why it's oxidative.
Do you write out what this is called?
This?
This again?
Vicinal dihalide?
Yeah, so this is a vicinal dihide. So, also note that even though we have a little partial positive charge here, that is not a carbocation, so there's no carbocation intermediate. Which means this is not subject to structural rearrangement from 1,2 hydride shifts or 1,2 methyl shifts. So if you have a synthetic problem where you have something like this, and you want to add some halogens around here for some subsequent chemistries, you would want to do something like this to accomplish it versus using hydrochloric acid, because if you use hydrochloric acid and you put a carbocation here, you're going to get a 1,2 hydride shift, and you're going to have a very different product because of it. You're going to be adding the chlorine over here. So if you have a situation where you are able to rearrange structurally because of carbocations and you need to avoid that, some of these other techniques are preferable. If you don't have the ability to rearrange the structure to form a more stable carbocation, then carbocations are perfectly acceptable.
So what's the dichloromethane doing?
Well, let's talk about that a little bit more. So what makes it possible is it's a good solvent for alkenes because it's just moderately polar / it's in the middle of the polarity spectrum. It's slightly more polar than chloroform, but not much. It's very similar to chloroform. And it doesn't have reactive oxygens on it. So a lot of our other solvents like alcohols and are reactive. Our acetones have ketone functionalities that can be reactive. Water is going to have the same reactive properties, and it's not going to be a very good solvent for alkenes because you're adding oily compounds to water, and that's just not, you're not going to get our reagents mixing very effectively. So the dichloromethane is just a good inert solvent. By good solvent means it dissolves things that we need to dissolve for the reaction to occur, and it's inert, so it doesn't participate. However, let's say we don't have that and we use water. And we'll pretend or just assume that for whatever reason, our alkene, we can get it into aqueous solution fairly well. What this is going to do is we're going to enter a new type of product called halohydrin. Because what happens is the very first thing is our bromine comes in, we do this concerted reaction, and we form this three-membered cationic bromine that wants to get secondarily attacked. But if you think about the amount of bromine in solution versus the solvent, we're going to have competition now where we're going to have a little bit of bromine floating around, but we're going to have a lot of water floating around. And because of that, water is going to be able to do a second nucleophilic attack more frequently than the bromine. Same mechanism, ring opening. And then we get our follow-up reaction where water comes in, pulls off the proton, satisfies cationic charge, and we're going to have acid as a byproduct. But this is super acidic, so it can do it because this is so acidic that this can act as a base. There we go. And so this is a halohydrin where we're going to have the halogen adding to the less substituted position on one side, and on the opposite side, the second attack on the more substituted position, we're going to have a hydroxyl group. So we're going to be making an alcohol with a halogen next to it.
Does water add an anti-passion as well?
Mm-hmm. It does. So in this case, you're not just going to have, you're going to have some we're going to talk in a few minutes about the difference between regioselectivity and stereoselectivity. And this is going to be both because the hydroxyl is going to be adding at the more substituted position and from the opposite side from the first attack. Now, the thing is that we're going to have a mixture of products with that because the bromine could attack from this side. It can equally attack from this side as well. So if this was a ring structure and we have freedom of rotation here, but if this was a ring and we kept something on the same side when we added from one side, if we add the bromine from this side, the water has to attack from the back side. If the bromine attacked from the back side, the water would attack from this side. So you could get two different combinations of products because of that. And if we had a methyl here, the bromine would end up on this carbon and the hydroxyl would end up on this carbon because this carbon's more substituted. So we could end up with a combination of this plus that. This isn't limited to water, though. We can do these with alcohols, too. Everyone's like, yay, variety! So any alcohol, we'll just use methanol in this case as a solvent. Same issue. We get our first attack with the bromine. We have this reactive intermediate. Now we've got alcohol as a solvent. Exactly the same mechanism. Except CH3OH. Okay. And now we have an ether instead of an alcohol attached to the more substituted position, anti-addition to the first attack with the halogen. So when you are describing this reaction, let's say you're describing some synthetic pathway because you're going in some 3 or 4 step synthesis, the solvent you define is going to be incredibly important because if you are ambiguous about the solvent, there's points on the table there. You have to say what the solvent is because the product is dependent on the solvent. It has to be an inert solvent if you want the vicinal dihalogen. If you want to have a halohydrin or alcohol or an ether, you have to make sure you put that in as your solvent. Questions? Yes.
Is your solvent, like this alcohol, is that considered a reactant?
In this case, it is.
Okay, so
Yeah. And
why wouldn't you just put it on the other side of the equation? Because I mean, like, why wouldn't you have it just on the other side of the arrow with the bromine? Because you're adding all 3 of those together and they're all reacting to each other.
well, because it's the solvent. But maybe, to get a little clarity, it's both, so you have to put it someplace. And this is a reactant too. Now, here's the thing. You're going to have a little bit of your vicinal dihalide forming also as a minor product here. It's not going to be 100% outcompeted. So if someone was to ask you for a major and minor product, you have to count for both.
Mm-hmm.
So because we already have a reactant here, it's not like you're going to have a reactant here and a reactant here, like 2 reactants piled up. So it's easier to say we've got this plus, it would be cleaner to say we've got that versus this plus this plus this.
Yeah, because writing it like that assumes you have a lot more CH3OH than Br2, right?
Yeah, so you know that this is, and that's a good point, is if you're treating it like a reactant that you're adding, that would say that maybe something else is the solvent. Where you'd be, say, trace quantities of this in that. Dimethyl chloride.
Thank you.
Dichloromethane, excuse me. So whenever you put it in as a solvent, you also know that you have a huge excess of it available as a reagent. If you lift it as a reagent, you're not necessarily going to assume that you have a huge excess of it or that you're doing the reaction in it.
Wasn't I writing out that mechanism? Do we need to show that bromine ion just floating around as a
No.
finished product? Okay. Just
Not unless you're showing the mixture of products.
Just with
Yeah, if you're showing it as a mixture of products, then you'd want to, but
So I get that the solvent would produce a vastly greater quantity in the reaction, but there would still be as an extremely minor product.
the vicinal product,
Yeah.
because it's still perfectly capable of doing the reaction with that bromine.
we have another question.
Oh, it's a polite hand. It's like, hi.
So the first bromine that attaches, is that considered an electrophile and a nucleophile?
It is initially the electrophile because of this first attack. And then it has too many electrons around it because it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has to do something, and then the second attack is a nucleophilic.
And it's concerted, right? So it happens.
Right, so they're both, because as this is forming, it's exceeding octet and it has to do something with the extra electrons. So both of those things are happening together.
Could you form a reaction like this with something that's capable of holding more than 8 electrons in its outer shell and form a more stable?
You mean like inorganic compounds? Yes, but that's a different chemistry class. And this is the world of carbon, hydrogen, oxygen, nitrogen, sometimes sulfur and phosphorus.
Phosphorus can hold.
Schnapps.
Yeah, but phosphorus isn't going to be the center of this. Yeah, like phosphorus. We can exceed that. We can exceed these bonds of phosphorus. You can get up to 6 bonds of phosphorus, but mostly we're just looking at phosphorus as phosphate as a modifier. Like I said, sometimes phosphorus. But this is my plug for taking some more chemistry classes. Specifically bio-inorganic chemistry, everybody's favorite. Is there anybody in bio-inorganic right now? Yeah, we got one person. Don't tell them how great it is because you don't want to scare them off. The first test went really well, I heard. Yeah. I'm lying. Anyway. Sorry?
Should we run now?
No, only if you're a chemistry. No, I'm talking. How many chemistry? We got one chemistry major. Do we have multiple? 2 chemistry majors. Technically, kind of. Yeah, okay, but
Not really.
not really.
Just on the paper.
Yeah.
Just so you can get,
Yeah, so you can get access to classes before they're full. I know.
Yeah.
I know how that goes. And then when we were getting reviewed, they're like, "You don't graduate many of your majors." I'm like, oh, it's because they're using us for our degree title.
You're welcome.
I know. We're trying to set up some kind of system where people who have a degree that are post-backing don't have to declare a fake major. They can actually just enter a post-bac program that gets them priority registration like another major. So we can actually separate people who are actually pursuing a degree versus people who have to declare a degree to get into classes.
Right.
Because that just messes up everybody's data.
It messes up your guys'
It makes us look like we get rid of everybody before they graduate. They're like, wow, the minute everyone gets through organic, they leave. I'm like, to become doctors, not to like busk it on the side of the road. Even though
That should be
over the next 4 years, you may wonder, did I make the right decision? Busketing, medical school, busketing.
Yeah, really.
What is
Right?
busking?
It's playing music for money.
Like you're hoping
But but usually they have a bucket. And anyway, Google it.
I didn't know there was a verb for that.
Yeah, we didn't know there was a verb for it. We just knew.
It started a while ago because somebody what was the movie? It was who's the super angry Irish comedian?
There's a lot.
No, there's one in particular.
Mike Myers.
No, way angrier.
Okay.
What is the movie? And this particular movie,
Describe other things they might have been in that were.
wow,
relevant.
recently it's been mostly TV shows. What's the
David McSavage.
So there's it's kind of an obscure movie about a couple college kids who kidnap a gangster and cut off his fingers and hold him for ransom.
I vaguely wait. Oh no, there's a.
And the guy and that gangster's bodyguard is this comedian who refers to busketing, and then it actually got incorporated into the common culture of asking for money on the street corners using a bucket. And I had friends that did that in Seattle while going to grad schools. They on the weekends go make money by looking poorer than they were and playing music. But they were good musicians, so they did pretty well doing it. We've diverted from chemistry. Other questions about this blank board? Okay, moving along.
Thank you. That is actually really informational, and I appreciate that.
No problem whatsoever. And everyone, I was like, that sounds like a good idea. We could maybe go downtown and make a little bit of money.
I mean, people do that here.
Okay.
What? No? I feel like some places.
Okay, so we have to start worrying about, we've been using these really simple compounds that have, I know everyone's like, oh, thanks for telling us how simple this is. These really simple compounds that give us fairly specific products. We have sometimes a major product, sometimes a minor product. But what we're going to have to start paying attention to is combinations of products in terms of not just their formation of different types of compounds, but different stereoisomers as well. So in regioselectivity, you have a favored constitutional isomer. Constitutional isomers are isomers where you have the same molecular formula, but they are arranged differently in terms of how things are bonded to each other. So examples would be those major versus minor products we've been looking at, where we have one, let's say, carbocation intermediate, which favors a second attack on a tertiary carbon versus a secondary carbon. The tertiary carbon getting the second attack is going to be your major product. Your minor product is going to be on the secondary carbon. Those are constitutional isomers because you have all the same building blocks. They're just arranged differently in terms of their actual bonds to each other. Stereoselectivity is when you have a preference for forming stereoisomers as a product. So there will be cases where we will be forming specific, let's say we do an attack on an R compound, it will stay R. Or sometimes we'll do an attack on an R compound and it will get its stereocenter inverted and become S. What we'll be finding here in a second is if we have an asymmetric center and we attack it forming a symmetric center, that will have a racemic mixture, which is a combination of both R and S, and we have to be able to account for both of those things. So, oh, and then there's one more term, stereospecific. Let's say we have a combination of isomers where we have two stereoisomers of the same, what would otherwise be the same compound, and we do a reaction. Each of these stereoisomers will create their own stereospecific product. So let's say we make something we do this reaction. It has an asymmetric center. It produces both R and S stereoisomers, and then we do subsequent chemistry. We're going to end up with different products downstream too. So one of the, as we get into OChem, it's like layers. Just as soon as you get on top of like one of the layers, they're like, oh, you know what it is? It's like running, which I'm not a giant fan of. And you're running up a hill, and you're like, I'm almost to the top of the hill. Because you're on this part of the hill, and what you see is this is the top, but then the hill does this. And you're like, get here, you're like, oh, I'm not at the top of the hill at all. And then you get to this part, and you're like, oh, no, it's still uphill. This is still terrible. There's people who disagree with me. They like the hill.
Chemistry.
Yeah, I know. So chemistry is, yeah.
Still terrible.
It's still organic chemistry, and this is still fantastic. Yeah. So, wow. Except everyone picks their poison, I suppose. So this is my vision of what you guys are experiencing. I don't know. I have an odd affinity for this stuff. So as we do this, it's going to get, we're going to add layers of complexity to it, which will make it even more important that if you are feeling uncomfortable with any of this content, that you double down on that content you were uncomfortable with, because this class is probably more cumulative than any other class outside of a foreign language you've ever taken. So just because something's on the previous test doesn't mean it went away. It's probably coming back again in spades. So let's look at this as an example. Okay. Let's do our very first most familiar reaction. If we react this propene with hydrobromic acid, we're going to get our first attack grabbing this, kicking off the bromine, second attack on the more substituted carbon, and we should get as a product this compound, which is achiral or chiral? Achiral, because we don't have any carbon which has 4 unique groups around it. However, if we do the exact same reaction, but we have an extra carbon.
Chiral.
Yes. Now we've got a chiral carbon. And so the question is this chiral carbon going to be R or S or both? In this particular case, it's going to be a 50-50 or nearly 50-50 mixture of both. And the reason is because when we go into the intermediate, we have this carbocation. What kind of orbital is housing this carbocation? Where is this positive charge residing? Empty p orbital. I'm going to revisualize this so it's a little more. There we go. We have an empty p orbital. what is the three-dimensional orientation of the three groups bound to the carbon? Trigonal planar, right? So we don't exactly have any groups downward or upward that would bias an approach from a secondary attack. If these groups were all down here, it would mechanically be hard to get a second attack to the carbon, and it would bias attacking from the top. Vice versa is the same. But because it's trigonal planar and we have this vacant p orbital that has a charge that wants some electrons, we can come in for the second attack up here or down here equally as well. And because of that, we're going to have two different products. If we come in from on top, it's going to push all of these downward. And if we come in from underneath, it's going to push all these upward. So in this case, if we're prioritizing, we would have 1, 2, 3, 4 R, or we would have 1, 2, 3, 4 S. So because of being able to attack either face, we're going to have a 50-50 mixture of R and S. And this is called a racemic mixture. Where the two species are called racemates. And this leads us to a really important rule. If you do a nucleophilic attack or you do some kind of addition reaction to a compound which is achiral, and that attack leads to the formation of a new chiral center, whenever you start achiral and you're doing an attack that makes a new chiral center, you're going to end up with a racemic mixture. Sometimes you won't have a perfect 50-50 mixture, but conversationally you'll be close to 50-50 for these racemic mixtures.
Wait, okay, so you said if you nucleophilic attack.
So any kind of addition reaction that forms a new chiral center, whereas you didn't have one before.
Ah, okay.
So if you're starting achiral, you do a reaction and you now have a chiral center. Because you started achiral, you're going to have a... the exceptions are enzyme-mediated reactions, because enzymes can do things that we can't do in a test tube, unless we use enzymes in a test tube, which we do occasionally, particularly when we're making drugs. And this is really important because a lot of what we're doing in terms of organic chemistry is pharmaceuticals, and because enzymes are highly specific to recognizing specific stereoisomers, it's not unusual for us to make drugs where half of the drug is one isomer and is inactive and the other half of the drug is active. Now, I'm trying to think of, I don't remember if it's Tylenol or ibuprofen. One of those two is a racemic mixture when you buy it, and so only half of what you're taking is actually effective as anti-inflammatory or painkiller. However, the other racemate is benign in terms of its biological activity. There's some pretty awful examples of before people were really acutely aware of different biological effects of unintended consequences of racemates. Now I'm blanking on it. It's thalidomide. All the negative side effects of thalidomide weren't because of the intended drug, it was because of the racemate, which wasn't tested for toxicity. So the racemate was what actually caused all of the birth defects associated with thalidomide. So racemic mixtures are really, really, really important because unintended products aren't necessarily benign products if you're talking about pharmaceuticals. So how does this play out in terms of, let's see, a couple examples. Any questions about this before we do some make it even funner?
Why is there still a charge on both?
This one?
No, where's the
Oh, there shouldn't be.
Okay. Just checking I'm not crazy. Alright.
Not crazy about that. We're all a little silly sometimes. Any other questions? No charge up. One of these days I'm going to do an entire organic lecture where I don't have a charge someplace it's not going to be supposed to be. Probably right before I retire. No? Okay. What I'll probably do is I'll just have to make a PowerPoint and then it'll be perfect. I can't even imagine teaching organic chemistry off PowerPoint. Here's a reaction. Bam! Any questions? Good. Click.
You just have to do like one of those things where it has animatics, where it draws it up step by step, which would be awful for you. But it would be great for us.
It's a joke, but that was how my calculus class was, so it's not funny anymore.
Here's some calculus. Bam!
No.
You start laughing.
Yeah, we're just like laughing at our pain. We've been through that.
Okay, so let's do... Do we have any chiral centers in this first compound? That is chiral. It's going to be unaffected by the reaction, however. So what we're going to be doing is adding a second chiral center to this compound with this reaction. So we're going to do the first attack, make a bromide. Bromide's going to come in and do the second attack on the more stabilized position. Note that we have a more substituted carbon and less substituted carbon, so the bromine's going to have to end up here. So we're going to end up with a couple different compounds. So, what's the stereochemistry of this compound is, of that carbon? Is it R or S? How about this one? You like R? Oh, yep. So what are these two compounds to each other? They're diastereomers. They're non-superimposable, non-mirror images. So, if you have a compound which has a chiral center, and then you create a new chiral center where there was not one, you will end up with a pair of diastereomers, which are two distinct compounds chemically. You can separate these on a column. And so, if you were asked to predict the products of this would be the correct answer, not Well, this would be worth some points. Because you put the bromine in the right carbon, but you didn't identify where it is spatially.
Would these appear in equal ratio?
Yes. Because this is not a large bulky group which will substantially prevent attack from either side. But it would be close to 50-50. Functionally 50-50.
So would it be incorrect to just put one of those diastereomers as your answer to the product?
It would be 50% of the product.
Okay.
Yeah. Yes.
So if you threw like a terbutyl group there instead of a methyl group,
Mhm.
that would skew the ratio more one way or the other?
It could skew it to have the second attack from underneath slightly. You might be looking at a 60-40 or something like that. Not perfect 50-50, but it's still going to be considered a racemic, close to racemic mixture of racemates. Yes?
Why is the asymmetric center with the bromine R configuration when the high priority group's unattached to which?
I don't know. Did I do it wrong? Too many red things going on here. Let me get rid of... It's like orange is different than red. Maybe I'm looking at the wrong. So we got our 1 group. That's going to be our 2, 3, 4. 4 is forward. So what? 1, 2, 3. So if this is 4 is up. So let's see here. 4 is back. If this is a steering wheel, we'd be going left, but because the weakest group is forward instead of backwards, it's up. Yeah, it's R.
Oh, I see. Okay.
Yeah. Okay. Throwing charges on bromines and making R's S's, except that I didn't, so it's okay. Whew. That was close. Nothing makes you second guess yourself when you're on the board, like somebody's saying, like, but why is that way? And you're like, I don't know. Is it? Well, shoot. During my master's defense, I had this really fantastic PhD advisor who is no longer, he has a great sense of humor. And I had him on my master's committee. He wasn't my advisor. And halfway through my master's defense, or was it my PhD defense? No, it was the master's defense. I'm going through some mechanism and pushing electrons and said, this position's oxidized to this. It's like, oh, whoa, stop. This is like, there's like 100 and something people in the audience. Like, stop. That's an oxidation. Oil rig, oxidation is loss of electrons. This is it's an oxidation. It's like, yes, that's an oxidation. Continue. Yeah, he thought he's super funny. After the fact, it's funny. In the moment, not so funny. But, yeah, he's a funny guy. Where are we? Okay, so let's do a couple different... we have just enough time to do this. We're going to talk about different stereoselectivities for the reactions that we've done. I've already talked about it a little bit. I just want to kind of go back and review. One of the reactions that we didn't discuss was catalytic hydrogenation on palladium carbon catalyst. So catalytic hydrogenation is just any time you've got a double bond. If you bubble hydrogen gas over a palladium carbon catalyst, you're going to saturate these positions with hydrogen. So you're going to make a saturated hydrocarbon. And this is typically just looks like this. Now, in this example, we have freedom of rotation, so where that hydrogen goes doesn't particularly matter because you're going to get a preferred 3D conformer based on what these other groups are. Now, if these are in a ring structure, however, there is some selectivity because you're dealing with this catalytic surface. This is literally laying on some catalyst, which is facilitating transfer of protons to one side of the double bond. So in this particular case, we're going to get Syn addition of the hydrogen. So let's say this is oh man, did I just do a 7-membered ring? 1, 2, 3, 4, 5, 6. Yep. Cycloheptane. Not going to do that again on purpose. Let's see here. 1, 2.
Just knock out a side.
Nah. No, we're rolling with it. We're rolling with it. Just gonna make this super easy. Yay! All right. So. Now I'm gonna have to do it again. Because it's Syn addition, both protons are going onto the same side of the double bond. So if you have a situation where you don't have freedom of rotation because of the ring, something like this, both have to add to the same side. So it can either add from the top, like this, and push both of the R groups downward, or it could add from the other side if this ring was flipped over and facing the other side of the or the other side of the ring was facing the catalyst, and you could have both of the protons added from underneath, and shoot, why not? Right. So you're going to have a mixture of products because of this, but you're going to have Syn addition for any kind of catalytic hydrogenation with a palladium carbon catalyst. Peroxy acids. Are going to have also have Syn addition. Doesn't make sense because they're coming from the same side. So this is considered Syn addition. However, subsequent attacks have to come from the opposite side of the ring for ring opening reactions. So the second attack will be anti to that first attack. But we don't have a lot of second attacks yet to use. Hydroboration, followed by oxidation. Is also Syn addition. Because of the mechanism with both sides reacting simultaneously in that concerted fashion. So everything's Syn except for the vicinal diol halide, which is anti-addition because one comes in from one side and the other has to attack from the opposite side. So if we have to predict the stereochemistry of this product, and it's not able to freely rotate as a product because we have some ring, let's say cyclohexene, and we do this reaction, and we have our inert solvent. That's going to be our product. I would normally draw a combination of products, except that if I draw this down and this up, they'd still be superimposable because of the particular product. If we did this one, ooh, let's do this. Wait, 1, 2, 3, 4. Let's do this. Let's predict this one. What would the product be? Go ahead and everyone take, since we have 10 minutes, go ahead and take a minute and see if you can predict, based on the mechanism, what this one will do.
Hypodramatic, sorry.
No, that was a little, well, yeah, like.
Got it.
For those who are watching on YouTube, somebody just rolled their eyes at me for putting that up on the board. Both eyes.
Is it possible to roll one eye?
Whoever is adding subtitles to this is going to have to add dramatic sigh in the background.
I mean, subtitles are fun. It'll end up probably being something like 2 stage behind you.
Probably. Okay, so let's go ahead and rationalize this first one. Where does the first attack come from? Double bond. Where's the second part of concerted attack go?
To A.
Why to A? Because of the partial cationic character. If it attacks from above, like this, it's going to push the methyl group down. And then we're going to get our second attack here from underneath when it ring opens. If it attacks from underneath, pushes the methyl group up. Actually, I shouldn't even have this as a wedge because that isn't a stereo center. That should actually just be.
That might help.
There we go. But because that's down, this has to be up. So we have a combination of products. And if we were to do this in methanol and form a halohydrin instead of a vicinal diol halide, the second attack has to go to B, and you get a combination of stereoisomers. For the ether. So everyone's like, oh man, we just had total control over these simple mechanisms, and now we're like, yay, it's more fun now. But yeah, now that just whenever you're doing these reactions, just try to pay attention to, do we have a stereocenter before? Are we creating a new stereocenter? By virtue of creating a new stereocenter, what kind of mixture of products might we have? Is it Syn addition? Is it anti-addition? Because that's going to be important. Do we have no freedom of rotation because of a ring or some other constraint? If we do, we have to show this. If we don't, then it doesn't often matter because freedom of rotation around a single bond sorts it out through the most stable conformer. So that is it for chapter. Are we in 6 or 7 right now? 6. Okay. So next week we have alkynes, so triple bonds, which have some unique chemistry because they're a little bit different in terms of their proclivity for reaction.